back to Old Steam Powered Machine Shop. This is episode number 41, and if you're a regular viewer here on this channel, you've seen this engine progress up through being a pile of parts on the floor that I dragged out of a woods. It was under a couple of pine trees covered with pine needles and had rainwater in it. And a lot of stuff was missing. To what we got here now. I got the flywheel moved over on the other side, and I've been working on it pretty steady this week, and got a few things done, but it's just amazing how much time it takes to do some things. I mean, you think, well, I can knock this out in an hour, and you spend half a day or most of the day on it. But anyway, in order to mount the flywheel on the other side, of course, the crankshaft is slightly different diameters on both sides, and the keyways are even different. So I had to bore out the center of the flywheel and bush it, and then cut keyway back. But that wasn't a real bad thing, because the center hole in the flywheel wasn't that good anyway. There were some casting flaws in there, and it's really not a very good casting. So it made it better in the long run. And over on that side, it gives a straight shot for the governor belt here, and it won't have to cross over and extend the shaft out to come down on the other side. These engines were sort of modular for Morris, in that they would build them either left or right, the flywheel on either end, for whatever, to go with whatever kind of machining they were putting them on at the time. And I want to thank you all for the comments. Last time were really good. A lot of good stories, a lot of folks introduced themselves, and I think anybody that goes down through those comments would appreciate reading that stuff. And we had some discussions on different things, and I really appreciate the input. The piston, of course, you saw in the last video, is all finished. The rings, right now, as we speak, Cattail Foundry should be casting them. Emmanuel King down at Cattail found, actually was a Frick steam engine pattern from the old Frick company for rings. It was I think for either 6 1/4 or 6 1/2 inch bore, because they're 6 3/4 OD and 5 1/2 ID, so they're a little heavy on the outside, about right on the inside, but they'll work fine. So what it will be is a cylinder sleeve about that long, and about an inch thick, that we can make some rings out of. And next video, we probably have to get started making a slide valve for this. It's got to be designed and figured out, and we'll get into that. I tried running all the dimensions through a Bilgram diagram, which I'll show you next time for doing that, but I was doing something wrong, and I couldn't get it to come out reasonably right. So we'll deal with that next time, and we'll get right to work. So thanks a lot.
I always figured that the big drill is the quickest way to remove metal from the hull. You can bore and bore and bore, but you can't keep up with a big drill. 173. And we gotta go to 162.5. That's gotta be right. Let's see, let's slow the feed down a little. Okay, I was a little heavy by about 1/1000. So I just tweaked it a little bit, put a little cutting oil on it. We'll go across with that. This is an old Armstrong tool. It's a gooseneck tool. It's split here, and it's made so that it flexes a little bit down away from the cut, and it makes it a lot smoother, supposedly.
was waiting for it to turn sideways and catch between the chuck blades. But it didn't. Here's the flywheel setup in the horizontal boring mill. I've got a couple of angle brackets here. I've played with this quite a little bit, and this is the setup. I made a tram here to go in a tool holder, and with a dial indicator you can swing it around. I'm going to try to line it up against this surface because it's the only thing I got to get it straight this way. The problem is my lathe is not quite big enough. I can swing this. This is 18 inches and my lathe is 18 inches, but I got no way to hold it. My faceplate isn't quite big enough, and there's no way to grab it with the chuck here because this is a curved surface. So I'm going to do it this way. I mean, the whole trick around the shop is to, if you got a machine that's down or being used for some other job, you sometimes have to do things on machines that would best be done on something else. But anyway, I got this, the indicator is reading 0 on these ends and about 2+ on the top and about 5+ on the bottom, which tells me the flywheel is warped just a little bit, and could be that I'm springing it some by clamping it here, and I haven't got it really super tight here because it'll actually spring the flywheel a little bit in here. So once I get this bushing board out, I'm going to make a short little arbor to go in there that'll be crankshaft size, and recut the keyway in here, of course, and then I'll be able to turn it in my lathe, and I'll be able to face off a cosmetic and true up on the sides and here, because this is pretty pitted up here anyway, and I had been planning on doing that. So this gets it lined up this way. Then to get it lined up axially, I got another setup. Knock this one out of here. Oh, it's low right there. And it's a little high right there. So, need to crank the table that way, a couple thousandths. I'm not gonna do it. Looks pretty good side to side. This indicator has a scale on both sides, so you can read it either way. Makes it kind of handy. That's about 2 thousandths negative there, and about 5 thousandths positive there. So it's got to come up just a tad, I think. Down. Oh. Yep. Gotta come up just a little bit. And when you're doing this on an old machine, you can't dial it in and then lock it down, because when you lock it down, it's gonna make it move. So I've got the cross travel on the table tightened down, and I'm just working against it with a crank. And the same thing here. This locks the spindle travel this way, and I've got that tightened down some, so I won't have to go back and retighten it and disturb it. So what we'll do is we'll come up just a, let's see, elevate, that's this one. Just a half a smidgen, if it will. Yep. And the other thing is, you always want to crank in half of your error. That way, half of it will go on one side and half on the other side. Okay, so that's, I don't know if you can see, but that's pretty close to the 0 there, 0 there, 0 there, and 0 there. So we're lined up this way now, and we checked it with the tram this way and this way. I put a little shim, let me back out a little bit. I got 5,000 shim up on the top, which gets it right this way, and then by tapping the angle plates I can get it right this way. So it's pretty close. This is set up to bore the bushing to final size in the boring mill. I'm going to do it a little different than the setups you've seen before in this boring machine. I'm using a boring head, and this is an attachment that's usually used like on a vertical milling machine like a Bridgeport. They've been around for a long time. This is kind of an old one, and it's probably the same vintage as the boring mill. I didn't have an adapter to fit number 4 taper that would work with this, because it had, for some reason, it had a very oddball thread. So I wanted to get it set up as close as I could to the spindle and as rigid as possible. So I spent 2 days making these plates. This is a drive ring that bolts to the, not the spindle, but the spindle drive sleeve. And then this is bolted to the boring head, and they're both piloted on the quill. They just slide over and bolt down. So this should be very, very rigid. Like later model boring mills, well, and some of the early ones too, all of this was built into the machine. They had a head on them that had a dovetailed slide that would move a bar across. And this is just a plain Jane machine for some reason, and it never had any of that on it, so got to use a boring head. This is just a high-speed steel tool in a homemade bar here. It fits in here, and the way it works is it has a dial that works with a Allen wrench, and if you can see, it moves it in and out. The dial is laid out in thousandths, but it actually is half thousandths, because if you dial in 10, it only moves it out 5. to give you a 10 thousandths difference in diameter. It actually is what it is. And then of course you lock it down. And the big thing you're fighting with this is chatter. No matter how rigid a setup you got to be careful with your tool point, that you keep the point real pointed and not broad at all, and except maybe for finish pass. We'll see how it goes. This is really just mild steel, but I've got a real sharp point on this, and I'm going to take some fine passes through there and hope I can get through it without any chatter. One 931. Got 5 to go. So we'll bump this up 5. Out of the way so I can turn the crank.
Okay, what I'm doing here is making an arbor to swing the flywheel on. So this has got to go down to the side of the flywheel here.
This is an instrument that would have been found in any high-end machinist toolbox in 1925. It's a number 64 Starrett universal test indicator, and it's the forerunner of all dial indicators. It has a kind of a clever arrangement here on the end where you can set it up to push that way or push this way or flip it around. The spring, the little leaf spring or wire here, can be reversed by flipping this little knurled knob around. It's a test indicator. I don't have all of the fixturing for it. This is just something that I made to work, and I'm going to use it to indicate the flywheel with. There you can see that's about 15 thousandths off that way. And in this direction you can see we got about 6 thousandths. You know, you think this looks pretty slow. It's actually 22 RPM, but if you figure the surface speed at the outside of this is 18 inches in diameter, and I figured it out. 18 inches is a foot and a half. So it's 1.5 feet in diameter times pi is 4.71 feet around. So you multiply that by 22 RPM and you get 104 feet per minute, which is kind of in the ballpark. It's about right for carbon steel tooling, and it's just a little slow. I've seen it published for regular soft cast iron where it should be no more than 120 maximum feet per minute. So it shows you when you're turning something big diameter, you got to watch the speed. Switching cars with them all day, you know, flipped it around on the other side, face off this side.
Quitting time.